question 1 from tutorial 13. Okay, looks tough, but actually applies the principles that we have learned just now, principle 1 and 2. Okay, so let's look at the part A, part 1 to part 5 parts. Let's look at part 1. Quite simple, right? What's the relationship between I1 and I4?
They are the same by the first principle.
Yeah, okay, because I1 goes to the battery and come out through I4 at the resistors, right? So
Yes.
it's actually, yes, very good. So I1 got I4. So the principle is which principle?
The first one, total current equal to total current out.
Okay, so do you need me to write down for you?
No need.
Okay, let's go to part 2. Okay, relationship between I1, I2, and I3. Which relationship again? What principle?
The first one is the same.
Yeah, so
In equals to out.
So is?
I2 equals to I1 plus I3.
Perfect. Okay, let's look at the part 3. Oh, we're going fast. Okay, what's the relationship between E1, V1, and V2?
E1, V1, and V2.
So
That means
which
we are
loop will
looking
you
at
take?
which loop? The left or the right? Or left, yes.
This one, right?
Yes.
Okay, this loop. Okay, so using principle number
2. Total potential rise is E1. Potential drop is V1 plus V2.
Okay, great. So it's E1 equal V1 plus V2, correct? Okay, so I erase this. No one else to confuse you. Okay, now let's go to part 4. E2, V2, and V3. So which loop will you take?
The other one?
Okay.
The other box, right?
Yeah, this loop. Okay.
That means do we draw the loop, direction of the loop according to the conventional current?
That will help you. In this case, if you draw the opposite, then your E2 and V2 and V3 may become negative.
Oh.
Okay.
But get the same answer lah.
Yes, you will get the same answer.
But
okay,
not
so
advisable.
So I draw this because the battery, the current, can you see the way we draw is in an anti-clockwise manner.
Follows the conventional current.
Yes.
Okay.
Okay. So in this case, what's your answer?
E2 equals to V2 plus V3.
Perfect. Okay. Okay, let's look at the last one. E1, E2. Wow, E1, E2, V1, and V3. How? It's like they're spread very far apart. But actually, you can see something, right? There's one more loop we haven't taken, right?
The big one?
Yes, we can take the big one,
The
ignoring the
rectangle.
central one. Yeah. Okay. Can you take this?
Oh yeah. Okay. That means okay.
So we're ignoring the V2, right?
Yeah.
Yeah, because it's not part of the loop. Okay, so what's your answer? Okay.
That means E1 total potential rise is E1 plus E2.
You sure?
Plus what? Battery I thought we plus together. EMF.
Look at the positive polarity for E1 and E2. E1 is positive here, negative here.
So how? Oh, that means the current will flow.
Are they helping each other or are they fighting against each other?
I don't understand that. Can you how
Okay,
does the current flow?
okay, take a look at this. Let's take the loop. The current should flow in a clockwise manner. So E1 will provide a potential rise, right? Because its positive polarity is, is over here, right? And actually drive the current in the same direction as the loop, right? So E1 should be positive, correct?
Yeah.
But E2, can you see that the positive polarity of E2 is on the left? So it will try to drive a current to the left also, right? So it will be against this loop.
Oh,
Correct.
okay.
So in this case, the potential rise, is it E1 plus E2?
No, E1 minus E2.
Yes, it must be E1 minus E2, correct?
Oh, is it because the E2 will produce a current that will sort of cancel the E1 current partially?
Yeah, it's like putting two batteries side by side but in opposite to each other, right?
Okay.
How about V1 and V3? Now V1, will you put positive or negative?
V1
Potential drop now.
drop.
Yes.
Negative?
V1 negative.
Positive?
V1 should be positive, right? Because can you see the conventional current out of V1 is actually the same direction as the loop direction?
Okay.
Can you see this current?
Mm-hmm.
The current direction is the same as the loop direction, correct? So the potential drop is V1. Okay?
Okay.
But V3, can you see that V3, the current through V3 is actually in this direction? You follow this one? Can you see? the current is actually flowing in opposite direction as the loop, right?
Okay.
So in this case, the V3 will have to be negative because the current is flowing in the opposite direction as your defined positive, your loop. Okay, so this will be V3. Okay.
Oh.
Okay, so that will be for question 1. Is there any problem?
No.
Okay, great. Let's look at question 2 quickly. We only got less than 5 minutes. Okay, let's look at 5 light bulbs, okay, connected in series to a battery. Now, the lamps don't light up for a certain reason, so you use a voltmeter to test. Okay, there are 3 scenarios, okay, so you must explain what has actually happened, what is spoiled, okay, or what has happened, okay. So, right, for the first case, you measure a PD across the battery and it's 0. So, what could be wrong? PD across the battery is 0.
Battery spoil?
It could be, or you can say the battery is flat, right?
Oh yeah.
I mean,
In a
because the
nicer
EMF is 0, right? Okay, in a nicer way, yeah. Okay, so okay, that will be part A. For part B, how about if it's not the PD across the battery is 0, but it's actually a PD across every lamp except A. A, you get a reading of E. Okay, so what has gone wrong? 1.5 hours.
I don't know. Can you explain?
Okay.
Can you explain?
Okay. That means, right, when you put the voltmeter across F, you read
A or
0. Okay, across D also 0 until you put across A. Okay, you get a reading and it's the EMF of the cell. So what does it mean? What has gone wrong? Okay. The break, the part that's gone wrong, right? This point must be at A. Why? There must be a break at A. Why? Because if you look at the diagram here, if there's a break at A, let's say this is B, C. Okay, this is not a very good diagram. Why is there no F, no E here? Okay, never mind. Okay, I'm sorry. Typo error. Okay, so in this case, right, the break must be at A. Why? Because, let's see, if the break is at A, what happens when you put the voltmeter across F? Because the break is at A, right? Okay, the current through here will be 0. So PD across F will be 0 because 0 times resistance of F, correct? Is 0. So that applies for D, B, and C. Okay? But if the break, but if you connect the voltmeter across A, what are we doing? We're actually
completing the circuit.
Yes, completing the circuit. This is very similar to your what? Using a voltmeter to measure the battery directly, right? Then you measure EMF. So you're completing the circuit and now you're measuring the EMF of the cell. Okay, so in this case, the answer is the break happens at
A.
A. Very good. Okay. Now look at part C. PD is 0 across everything. Not only B, C, D, F. A also now. Okay. But E across the battery. That means it measures E across the battery. So is it a battery problem?
No.
Yeah, because the EMF is not 0, right? Okay, not like part A. But it's 0 across every lamp. So is it like part B where there's a break in one of the lamp?
A, maybe A is spoiled.
A is spoiled, then you will get the answer for B, right? You will measure PD across A to be a certain value, right? To be E, right?
Oh, how to do? See, I'm not sure.
Okay, so PD is 0 for every lamp, right? So there's no lamp that is actually reading E, right?
Oh, meaning that means there must be a broken connection
Somewhere.
from battery to the lamp.
Yes, but is it in any of the lamp?
The first one is just like if there's a blockage at the beginning of the road. You can't.
Okay, by
No
reading
car can
0,
enter.
by reading 0 at each of the lamp, that means there's no current flowing through them, right?
Yeah.
So there must be a break in somewhere. Okay, but it's not in either of the lamps because all of them read 0. So the break must actually occur maybe here.